Okay, we're going to go into new reactions of carbonyls now. We're going to look at other nucleophiles that will attack carbonyls. We're going to look at the reduction that is called the Wolff-Kishner reaction, and we're going to look at the Wittig reaction. In the Wolff-Kishner reaction, we basically take a carbonyl and change it to a methylene group. We reduce it down all the way, remove all the oxygens, and add hydrogen in place. The conditions for this are hydrazine and potassium hydroxide. The hydrazine actually makes an imine that we're going to learn about later, but the nitrogen does nucleophilic addition to the carbonyl, and then water is lost, and we make this imine right here. When treated with potassium hydroxide, there is a really cool rearrangement that occurs where the protons are transferred to the carbon and the molecules rearranged so that nitrogen is a leaving group. And nitrogen leaves as a gas, a very stable molecule, and it drives this reaction to completion. Here's an example of this. We have 2-hexanone. We're treating with hydrazine and potassium hydroxide. And what does it do? It basically, the Wolff-Kishner bites off the carbonyl and leaves just a methylene behind. So I want you to now try the same reaction, figure out what is the product of 2-phenyl cyclohexanone when treated with hydrazine and potassium hydroxide, and then determine what conditions would you need in order to reduce testosterone, shown here, to this compound, this steroid. Pause and restart after you've figured out the answers. Well, to take 2-phenyl cyclohexanone, which is right here, and treat it with hydrazine and potassium hydroxide, what's going to happen? We're just going to bite the carbonyl off. And I hope you found that to be relatively simple to do. In order to change testosterone to this compound, we're basically taking off the carbonyl and putting on 2 hydrogens. How can we do that? With the conditions of hydrazine and potassium hydroxide. We've learned that nucleophiles like Grignard's, negative charge here, does nucleophilic attack on the carbonyl. Hydrides in lithium aluminum hydride and sodium borohydride, where essentially you have a hydrogen with a negative charge adding to the carbon in the carbonyl, or having water add across a carbonyl under acid or base conditions. We've seen these. Now we're going to learn about some new ones. Other nucleophiles that will add to carbonyls are alcohols. The oxygen has non-bonding pairs that make it nucleophilic. Cyanide, the carbon in cyanide is nucleophilic. Amines, which have non-bonding pairs on the nitrogen. Ylids, this is an ylid is a compound that have a positive and a negative charge on adjacent atoms. And if I look at this compound, there is a double bond between the phosphorus and carbon here. It's a single bond, regular sigma bond, covalent, and then the second bond is usually depicted as a positive charge on the phosphorus and a negative charge on the carbon. That carbon is very nucleophilic and will add to the carbon in a carbonyl. And then acetalids, these are as nucleophilic as Grignard reagents and do almost the same thing. Poor nucleophiles are good nucleophiles. This is a list of good nucleophiles. Good nucleophiles can add easily to carbonyls. You don't have to do anything to enhance the electrophilicity of a carbonyl when you have any of these nucleophiles, the ylids, acetalids, cyanide, hydride, Grignard reagents, hydroxide, alkoxide, so an alcohol that's been treated with a strong base, hydroxide, you know what that is. Okay, all these are going to add to carbonyls with no encouragement. They add directly to a carbonyl. But we have some poorer nucleophiles that require that the oxygen be protonated before the addition can occur. Protonation of the oxygen in the carbonyl puts a larger del positive on the carbon, And so it becomes more electrophilic, and a weak nucleophile like water and alcohol that has not been, it's not an alkoxide, but the alcohol itself, or amines, those poorer nucleophiles are then adequate enough to add to a carbonyl after it's been protonated. So here is an example of a poor nucleophile being added to a carbonyl. Here we have an alcohol. Notice there is acid condition. It adds across the carbonyl. So this oxygen becomes attached to the carbon, and then there's proton transfer, and this hydrogen ends up on this oxygen, and we get this alcohol and basically an ether group here. This is called a hemiacetal. Aldehydes that have one alcohol added across a double bond are called hemiacetals. If I take a ketone and add the alcohol across the double bond, what happens is the oxygen does the same thing, adds to the carbon, that the hydrogen in the alcohol group does proton transfer to the oxygen of the carbonyl, and we get an alcohol and an ether group here, and we call this a hemiketal. Typically, we cannot isolate these. The equilibrium is highly favored to go back to the carbonyl unless you have a huge quantity of alcohol and you're removing water. In that case, something else happens. But the hemiacetals and hemiketals usually cannot be isolated unless they form a ring when they're formed. So if you have, let's say, a 5-hydroxyl aldehyde, what will happen is that alcohol can turn back on the aldehyde and make the hemiacetal, and those sometimes can be isolated. Here's the mechanism for the formation of a hemiacetal. Notice the oxygen is protonated. An alcohol, here methanol, adds to the carbon in the carbonyl, and these electrons then jump up, and we have this structure down here formed. Then you have proton deprotonation, for instance, water or another alcohol would pull the proton off this, and you get this hemiacetal. Notice, alcohols are poor alcohols, and you need to have protonation by acid. Once a hemiacetal or hemiketal is formed, if you have more alcohol in there, what can happen is the acid can protonate the alcohol group here. Once it is protonated, that becomes a good leaving group, and it forms a positive charge right here. Once that positive charge, the water leaves, it'll form a positive charge here, and then the alcohol can come into that carbon. If it's, of course, you would have an intermediate of a positive charge, not shown here. So the alcohol then comes into the positive charge on the carbon and forms this protonated ketal or acetal, and then the water or an alcohol would deprotonate it. These are all equilibrium reactions. So how is it we control these reactions? Well, if we want the hemiacetal to form, we can actually make it form by pulling water off the system and having excess alcohol. If we want to go from the acetal or ketal back to the carbonyl, we just add lots of water and remove the alcohol. So here's an example of this reaction. If I want here would be an acetal because it was an aldehyde. If I want the acetal to form, I just use excess methanol and remove water by distillation. You form an intermediate hemiacetal, but then the acetal forms. You see, here is the carbonyl, and here is the alcohol. You'd have two of these, not shown. There would be two of these, and the alcohols add across the double bond. You see where the double bond was, you have now two single bonds to oxygen. And this is called here an acetal. If it were a ketone to start with, you would have a ketal when you finish. So, carbonyls require 2 alcohols, acid catalysis, and we make either an acetal or a ketal. So the acetals and ketals can be isolated if we drive the reaction to the right side. If we want to reverse that and take it to the carbonyl, we can do that by adding water. So this mechanism, this reaction right here, this equilibrium, we manipulate as needed. Whatever we want to have happen, we can manipulate the reaction. Acetals, ketals, hemiacetals, and hemiketals, I expect you to be able to identify what type of compound you have when you have one. What we do is we use the acetals and ketals often for protecting a carbonyl when we don't want to have nucleophilic attack occur on them. So what we do is we form the acetal or ketal, we do a reaction, then we use water and acid to deprotect the carbonyl. A common protecting group is 1,2-ethane diol, also called ethylene glycol. Here's an example. This is the 1,2-ethane diol or ethylene glycol. If we take this, we can treat this with one equivalent, an acid, and the more active carbonyl, the aldehyde, would then be protected. I could then do a reduction with lithium aluminum hydride, which normally would do both, but because this is protected, it won't be reduced. It reduces only the ketone, and then I treat with acid, and the protecting group comes off, and we get the aldehyde back.